I worked on MC techniques estimating the parameters of a pulsar related to LIGO data. It was based on a model of Rajon. And this was actually the major part. And 1 year I worked on sounding out the possibilities using MC techniques, and especially reversible jump MC techniques on LISA data. So, okay, LISA is an all-sky monitor, leading to a tremendous data analysis challenge, and with up to 100,000 potential sources. And we aim for filtering out these background signals in order to focus on the more interesting astrophysical events. So this approach is not a source abstraction approach, nor a grid-based template search using optimal filtering. This approach is supposed to identify and characterize periodic signals in the data. Then the signals that are sufficiently large in amplitude or have enough energy contribution, from these signals the parameters are supposed to be estimated, and those sources that are below a certain threshold are contributing to the noise. And one task is also to estimate the overall noise within the data. So the objective is, we started with a simplistic problem. It's just for sounding out the possibilities, as I said, as I mentioned before, sounding out the possibilities to use reversible jump Markov chain Monte Carlo methods on LISA data. And this is basically a Bayesian spectrum analysis. Though I use simplified signals, means sinusoids embedded within noise, white Gaussian noise. And we aim for estimating the number of signals. That's the essential thing. So the number of signals is unknown. Then we aim for estimating the noise variance and the parameters of the actual sinusoids or signals. We use a Bayesian approach, and this one is focused on the confusion problem. There's been work done before on Bayesian spectrum analysis, especially Jane's very famous Brethorst and Andrieux wrote in his 1999 paper a code, or explained a code about retrieving three signals within noise. But this is focused on confusion, so we will have many more signals. So the modeling is quite simple. So we have n data samples recorded at times t1 to tn, and d is the data vector, and the data is containing k superimposed sinusoids. And I'm using the Cartesian coordinate system here, so you could either express it like one amplitude and a phase, and I'm using the other way, like the two amplitudes and a frequency. So I have 3 parameters per sinusoid embedded within white noise, normal distributed with mean 0 and mean naught and variance sigma square k. And sigma is a parameter that needs to be estimated as well, so it's not known. So the model is for k sinusoids given here, like the superimposed sinusoids plus noise samples. And the class of models, I have n+1 models, comprising all these individual models for the k sinusoids. And each model has a parameter space of 3k plus 1 parameters, because I have the noise as well to estimate. So
you're always working presumably where n is bigger than 3k plus 1, right? data than parameters.
Sure. In my case, I have an example with 1,000 data points and 100 signals.
Okay.
Yeah. So the posterior, according to Bayes' theorem, is the prior distribution times likelihood divided by some normalization constant. And the likelihood is given here by e to the power of minus that's the sum of squared residuals, so data minus the model. And now we come to the priors. The prior distribution, we assume here a uniform distribution on a discrete uniform distribution on the number of sinusoids. Then we use an inverse gamma distribution with parameters 0.01, 0.01. So that's more or less close to the Jeffrey prior. So we can't. Jeffrey prior would be 0, 0, but it's not defined. So that's the same. That I don't know whether you know Winbugs. It's a code. That's a software under Windows to simulate from do Gibbs sampling, and
the proper prior distribution or
this one here.
Yes.
This one with 0.01.
Okay. So it integrates to prior.
Yeah. Yeah, and I use dimensionless units for the frequency, and I use uniform distribution on the frequency. So it's equally likely for the frequency and to have any value between 0 and 1.5. And for the amplitudes, I apply G prior. So that's basically a hierarchical model. So I don't know the variance of it's basically a normal distribution, a multivariate normal distribution on the amplitudes, with an unknown scaling factor, G square. And I'm using the identity matrix because I have so many signals here, like when I have 100, then this matrix would be a 200 cross 200 matrix. And if I would work with the covariance, I would have to invert a large matrix, which is not feasible. So I use the identity matrix here. Andrea used proper the 99 paper where Andrea coded the Bayesian way to estimate a spectrum. He used proper covariance matrix here, but this is not feasible. For the MC sampling, I use Gibbs sampling for the noise variance and the hyperparameter. I come to that later. Then I use different techniques for each set of parameters. So then for model determination, I use the reversible jump MC in order to walk within the multi-dimensional parameter space. And the delayed rejection for parameter estimation. So I'll come to that later. So for the Gibbs update, the Gibbs update, that's a normal. In a Gibbs sampling step, you sample from the full conditional distribution. This means, given all other parameters, I draw a sample from the actual parameter of interest. In this case, it's the variance. So given all other parameters fixed, I draw an inverse gamma sample of the full conditional, which is the inverse gamma distribution, in order to draw a sample from the variance. And that's how it works. So as I said, I use vague prior, almost non-informative, with alpha 0.01, 0.01, and beta, so scaling and factor and shape parameter of close to 0. And I draw a sample from this distribution, which is the full conditional. So here you can see full conditional. So here you can see the sum of squared residual, which goes into this distribution. So in a similar way as Andrew worked, I draw from the inverse gamma, which is the full conditional from the hyperparameter G square. And so the question was, what do we use here for the parameters for the inverse gamma function, inverse gamma distribution? So usually it would be straightforward to use alpha also like close to 0 and beta close to 0. However, I mean, when you take a look at here at this, in our case, the k is quite a large number, like 100. So these parameters don't really matter. So even this is a very coarse choice of inverse gamma function, of gamma distribution. And that's the same that Andrieux used. He played around with this. He used alpha equals 2 and beta equals 1 and 100 and 1,000. And it didn't really matter.
Could you tell me what hierarchical means in this context?
Hierarchical, you have this hyperparameter on top of the. You have this actual model, and on hierarchical, an extra level of where you have this additional parameter G square.
These would be the amplitudes of all the sources.
It's kind of, yeah, it's related. It's related to the signal to noise ratio in relation with the sigma square, with the variance. So these two are related to overall sigma. Yeah, it's basically kind of variance of entire, the kind of measurement of the entire amplitude pool. So yeah, I used to then sort of this reverse jump for model determination. So I'm working in this in a state space of different dimensionality. So okay. So in order to preserve the detailed balance equation, I have to what is this? Followed. Change this. Okay, so considering we are in model MK's dash. With parameter a dash k dash. So k dash is the actual current dimension I'm working in. The current state of the macrochain is. Then a reversible jump move has to be considered that preserves the detailed balance equation. So it's equally likely to walk within the dimensions. So, and this is done by dimension matching. So I have a random vector R sampled from a probability distribution function, so it's proposal distribution Q of R for proposing new parameters. And I have to use a transformation in order to work within the dimensions. And here in this case, I just walk within the neighbor dimension. So I just walk up or down one dimension. So one dimension means actually 3 dimensions. So I add up. So actually it should be 3. So either I add a sinusoid with 3 parameters, or I go down in dimension by 1 sinusoid, so 3 parameters. So without loss of generality, we can say k dash is k plus 1. So, and we use, I apply equal probabilities to move within the dimensions. So I draw like a random number and walk with the up or down in dimensionality with equal probability. So in this case, the acceptance probability for the reversible jump is given here. So I have here the prior, the likelihood. Here's this ratio is 1 when I use equal probabilities here. And then I have the Jacobian here, which is here. So the Jacobian of the transformation. So, and now we come to the strategies for the trans-dimensional moves in this case. So I use a split merge transformation, which means I either take one sinusoid and split it into two, or I choose two random sinusoids and try to merge it into one. Or I just create or annihilate one sinusoid. So that's a straightforward. That's what Andrew was using, and I added this because in terms of confusion noise, it's important to add this step, because you want to know whether a sinusoid, when you have two sinusoids very close in frequency, you need this step in order to figure out whether it's actually one or two. So the transformation for the splitting is given here. So when you see you have one sinusoid and try to split into two, so what you do is you half the amplitude. So take one sinusoid, half the energy or amplitude, and this random vector r is the perturbation between the two. So I create two, and the two new created sinusoids are slightly perturbed by this random vector, and that's the transformation. And this inverse transformation for this step, the acceptance probability is given here. The Jacobian is 2 in this case, and that's the acceptance probability for this step. So the inverse transformation is given here. So I have two sinusoids, I1 and I2, and I just add them up. And the vector r is basically the difference between these halved, because it's, and the inverse transformation is 1/2. And then we have the creating a new sinusoid, which is straightforward. The Jacobian is 1, and given here, the acceptance probability is given here. And the inverse transformation is the same, just I take one arbitrary sinusoid, and this vector r, or this vector a dash I from the randomly chosen sinusoid enters into this acceptance probability here. So the proposal distribution for creating, when I should see this, here's in the denominator, also enters into this into the annihilation process. So that's very important here for the reversible jump. So when you have in the case of splitting and merging, for example, this vector r here, when I try to merge two, this vector here enters into the acceptance probability, and uses also the probability density function used for the proposal distribution. So when you have too far apart, when you use, for example, for creation a very narrow distribution, then it's also in turn very unlikely to have an acceptance here. So this proposal, the proposal distribution is quite a tricky thing to figure out. It's fine-tuning. And the proposal. So, I mean, I explored the situation that I can use a Fourier transform of the data and create from this parallelogram. And also Andrea used this technique, so we can use a parallelogram for creating proposed distributions for creating new sinusoids, or annihilating them. Splitting and merging is done with a perturbation of the sigma, which we know from these parameters.
The parallelogram, of the measure the signal.
The parallelogram is Fourier transform, and then
of the measure signal.
Not the data.
Of the data. Okay.
Yeah, so it's straightforward.
Uh-huh.
So you can exploit it. It's much faster than this is really. I mean, just for 1,000 samples, the Bayesian spectrum analysis is really takes a lot of computing power. So that's the current noise level of the model K, which I can use for perturbing the sinusoids. And sigma f is from the Larry Brethaus book. He derived a term for these for deriving a variance for the frequency, and in this enters the signal to noise ratio, which I can use from the G prior and the sigma square. So the delayed rejection method is used for within model iterations. So the idea of the delayed rejection method is basically you have an actual Markov state n. The Markov chain is at an actual state an. Then you propose a move to a dash, and in case of rejection, you try another proposal. A timid step with another proposed distribution, usually a smaller variance or whatever, and then the acceptance probability for this state is given here. But in order to preserve the detailed balance equation, this idea is from Antonietta Mira. I don't know the papers. She worked together with Peter Green, and yeah, she wrote in a thesis about this delayed rejection method. So it's a kind of adaptive method in order to, but it preserves the Markov property. So the idea is, so you have a bold move, and upon a rejection of the bold, you try a timid move on, and that's the acceptance probability of stage 2. So this basically shortens a bit the burn-in period, burn-in time of the Markov chain, because at the beginning you have usually more stage 1 acceptances. So the proposals for the delayed rejection is it's just changed by the normal distribution with zero mean and sigma square, variance sigma square. Then the parallelogram again serves as a proposal distribution for the frequency. I usually split this, so what I do is either toss out to do a step within the frequency parameter space or in amplitudes. And in the second step, I either implement a step that incorporates the correlation between two sinusoids. So I use a multivariate normal, this covariance matrix, but only of a pair of sinusoids. So that's feasible computational-wise. And so the covariance matrix is derived by the basis function of the signal. The second stage for the frequency is based on this idea of Larry Brethaus, where you estimate the variance of the frequency regarding the signal to noise ratio. And now we come to the post-processing of the MCM output. That was the most problem, I would say, because when you have a reversal jump MC, you don't know, due to the switching and swapping or whatever, which sample actually belongs to which sinusoid, especially when you have overlap in the frequency. So what I usually do is I consider one model in the after the MC output has been generated. I consider the model with the highest posterior probability. I will show this in an example later. And then find the allocation of the M elements of each vertical jump to the M sinusoids. So when I consider just model M hat, then I have for each MC output sample, exactly m hat samples for the individual sinusoids. So in the literature, there are usually three ways of identifying the sinusoids. So it's identifiability constraint. That works well when you have just a handful of well-separated signals in this case. So what you do is just order by the frequency, because usually the frequency is the most the important factor of identification for the sinusoids. Then you have relabeling and label invariant loss functions. That. So identifiability constraint, as I said, it just works properly when you have well-separated sinusoids and just a handful, like Andrea used this technique. And yeah, so the model contains, unfortunately, more than m. And the problem is that when I have a lot of sinusoids involved, model m hat doesn't necessarily contain exactly m hat sinusoids. I encounter like blended sinusoids, and I will show this later. So I have basically a sinusoid that pops up in a model, then you go up in dimensionally, come back, and then you have another sinusoid. So I have this big mess around, especially when you have 100 or more. So in the beginning, I used like relayer algorithms. So I used kernel density estimates, found the peaks, and then tried to find the number of signals within this peak, because sometimes they overlap. But it's a kind of k-means type clustering where you start with some arbitrary cluster, then you optimize regarding the permutation, and then regarding the means. And the problem is here, like normally k-means, we have here the problem of permutation restrictions. So each sinusoid has exactly m heads sinusoids, and I know for each sample, Monte Carlo sample, that each sample belongs to another sinusoid, and I have to follow this permutational givenness. So the problem is, due to these permutational restrictions, it's very computationally expensive when the number of clusters or sinusoids is large. And also we have the problem with blended sinusoids, and they have multimodal appearance. So in the end, I used this technique here, label invariant loss functions. So it's kind of frequency interval separation. So the idea is to find a loss function that depends on disjoint frequency intervals and their resulting occupancies. So what I do, I have this an example. So I have here the output. So this is an output of model like with 5 sinusoids. So for each MC sample, I have exactly 5 parameter triples, so 2 amplitudes and frequency. And what I have to do is, it's really hard to separate those into like exactly 5 sinusoids, because this one is a kind of blended sinusoid. So this has low evidence, and there are other samples found in other areas of the frequency band. So what I do here is I have to create a loss invariant, this label invariant loss function, and this works like account for a certain given frequency separation here, or frequency interval, disjoint frequency intervals, the single occupancies within these intervals. So in this case, for example, I have exactly 1. Here I have, there's sometimes no, here that's no occupancy, sometimes 2, and so on. And I want this type of the frequency ranges that maximize the single occupancies. So I can have this, for example, or this, or this. And these are basically parameters here, the interval boundaries. And this is the label-independent loss function. So I count basically the single occupancies, in which L components of the interval follow into a frequency interval ik with these boundaries. And yeah, and that's the sum of the single occupancies. Once a single occupancy. And that's a global minimization problem, so I had to write another, like I used MC methods again. And I used techniques like varying the interval boundaries. I was proposing boundaries from the midpoints of randomly chosen RJ-MC samples. And so different techniques and proposing place. And then I was replacing boundaries in adjacent interval with deficiency between boundaries. So sometimes when I have here the plot, and if here's something, when there's a deficiency, then it's then I place the boundaries into areas where are a more higher occupancy, with higher occupancy. So I run this, and then in the end I get some the optimum interval separation, and then I can start counting. In this case, for example, so this is 1, this is 2, 3, 4, and so on, so forth. And here in this case, I don't know. I can't identify these samples, which of these. But I have additional information, namely the amplitude. So I assume that when I have high energy contribution, the signal is more likely to be eligible to be within the frequency interval. So in the next step, I can identify those who have higher frequency energy contribution. So now I can see here, now you can see a structure that number 4 seems to be a blended sinusoid. So there are lots of samples here which belong actually to 4. And so I used this abundant information to fit like a multivariate normal. A multivariate normal distribution. So the abundant information allows further allocation of the ones I still don't know here, the question marks. And the problems are the blended sinusoids, which are basically consisting of more than just one sinusoid. So in using a mixture distribution, though it's not a mixture normal because I have the blended sinusoid. So what I was using is a mixture of norm distribution and uniform distribution. So the normal distribution approximation for the core part of the sinusoid, so the actual sinusoids samples that belong to a sinusoid, and then the blended part is modeled by a uniform distribution, as I said. And so I have these two proportions, and I can estimate all these from the given separation. And in the end, I have this idea of this approximated distribution, and then I can allocate it in a final step to a certain to this mixture model. And so the advantage of this is for each sinusoid, when I have an reversible jump sample with m samples, for each sample belongs to a different sinusoid. It's not just chucking in all the samples in a big bucket and then try to work with the kernel density estimates. That's what I did at the very beginning. And so now we come to some simulation results. So I have a data set with 1,000 samples, and within this 1,000 samples I have 100 sinusoids. And I just draw randomly sinusoids here with a normal distribution with variance 1 and so on. So this is the signal to noise. So these are the 100 sinusoids, and these are the signal to noise ratios. So if one very weak, then these are weak as well. But these were randomly chosen. That's what looks so. It's not hand chosen. And I have 1,000 samples, and the noise level here is sigma equals 0.6 in the data set. So after 2 days, got this. So 2 days of simulation, like I think 500 million iterations, and thinned out by 1,000, so 500,000 iterations that I could use. And so I have 100 signals, so the highest probability is 99. And these are the noise levels that are core to the different models. So the higher the model order, the less noise level I've got, because the more simple a model is, the more these sinusoids which are lacking in this model, for example, contribute to the additional noise here, and that's why it goes down as well. And this is for with the highest, the model with the highest posterior probability, and I worked with this particular model. I also looked at this, for example, but this is the model of main interest here. So on the noise level, this is the credibility region of the 95% credibility region of this of the noise level. Yeah. So these are the frequency intervals that were calculated with this technique, with this interval separation technique. So my thesis, I printed all of them. So I have here a single occupancy of 99.51 and so on. So that's a pretty clear sinusoid and so on. And there's one here, 95.8, 94.8, and here's one only 13.72. So that's apparently like blended sinusoid. I don't know, I call them blendoids. Doesn't matter. Original phantom sinusoids, but one of the referees didn't like it because it's basically a blend. So yeah, so I have to take a closer look to this sinusoid here. Sorry. So that's a photo of the blended sinusoid. So these are the samples. So as you can see here, they are spread over the entire frequency band, like some other peaks. And this one is a close-up of just this very small region. And the amplitude is quite small here. And I think this is about 13% of the entire probability mass, and this is 100. And it's really hard to identify these when you just chuck in all the samples into one bucket and try to do kernel density estimate, because you end up with these all little tiny peaks. So and that's an ordinary sinusoid. S must go. Oh no, there are two. Yeah, sorry. So this is a well-separated sinusoid. So it's pretty smooth posterior distribution here. So I have here the frequency, the amplitude. So I have these three plots are for the three, like a cube from different sides, and then I have on top the square root of the squared amplitudes, sum of squared amplitudes. And this is a close-up of two sinusoids which are very close in frequency, and you can see the interactions between the posterior distributions. So when you come close, then the amplitude tends to get very large. Scheiße. I don't know what this is. Okay. Yeah, and these are. I try to find an appropriate way to plot all these 100 sinusoids, and the only way I could do is like zooming in sequentially. So I have the 100 sinusoids here with posterior distribution. The red crosses indicate the true parameters. So I have energy here and the frequency. So I calculate the energy from the two amplitudes in order to be able to plot this. And then I zoom in here and a further zoom in. And yeah, this is the concording parallelogram. And the same scaling on this. And so this is a parallelogram. It looks like this, and as you can see, the Bayesian spectrum analysis is capable of finding the two different, identifying the two different sinusoids. Whereas in the parallelogram, you don't see that there might be two. So it's I think it's half of a Nyquist step between those frequencies. This is a close-up of the posterior distribution again. So James derived a way to display a Bayesian spectrum, power spectrum. So because it's hard to compare these two, because here you have basically a two-dimensional plot, and this is here kind of energy distribution. And the idea was, normally when you have a theoretical spectrum, you have these power lines, which are delta functions. But in the Bayesian approach, both the amplitudes or the energy is known only with uncertainty, and the frequency as well. And Bayes derived the Bayesian power spectrum density by combining the estimation of the power and the spectrum line, the power in the spectrum line and the estimation of the frequency that are present. And no, this is just stationary. Yeah, that's I come to that. Yeah, but it's in an Outlook, so that's a problem. I have to go through all of shit. Press the wrong. More to move to. Sorry. Shit. I don't know how to jump to. That's the problem when you have these. The Bayesian power spectrum estimate is Bayesian's power spectral density is basically the expected value of the energy given a certain frequency times the probability density function of the frequency. And this is how it looks like. So it's basically this plot. The same frequency interval displayed in the other way in the Bayesian spectrum estimate. So I also included the spectral lines, and the height is basically it's a delta function, but the height concords to the actual energy contribution. So normally it should be a delta function, but.
So the for example, the light blue thing is
it's a Bayesian spectrum estimate.
It's the PDF for this power.
Yeah, the Bayesian power spectral density. Yeah.
Probabilities. That's what I mean.
No, it's energy per. It's not a probability density function. It's energy per unit frequency. A probabilities density function would be integrated to 1, but this is the energy.
But the red one, for example, which is asymmetric, you associate that with a single.
Yeah. So the good thing is I can identify and know that this is one signal. And I think this is one that has just 13%, actually 13% probability mass. Because there are others, but these are very straight sinusoids.
What are the dot lines?
The dot lines is the parallelogram.
Oh, the dot line is true.
Yeah, the dotted lines are the parallelogram as a comparison, but on a different scale, energy. And Bayesian spectrum estimate is energy per unit frequency. So it's a little bit hard to compare these parallelogram and Bayesian spectrum.
How large is the bin? Just in the periodogram, there's a bin size, frequency bin. How large is the bin?
This one I calculate this way. With smooth frequency. So yeah, I didn't bin. I used Schuster. See, it's. I didn't bin. It's smooth, but how do you say? Huh?
What's the width of one of those lobes?
That was what I was thinking, but
It's not a Fourier. I didn't use the Fourier transform in order to. It's imaginary. I don't have it in the talk. I don't.
Isn't it 0.001?
No, but I'm not binning here. I'm using.
But 1 over t would be 0.001.
Yeah, 1 over 1,000. What do you mean? But it's I'm not binning here. That's what I want to say. I'm using the function the Schuster parallelogram function. It's a smooth function. The dotted line, dotted just, but it's not the bins. What I'm. I have to look it up. So I have other. Sorry, I have other. So I've, this is another area of interest here. I zoomed in, and here again the Bayesian spectrum analysis, the Bayesian spectral density. And that's a rather weak signal.
Do you find that the parameter estimation fails when two signals are closer more often than
Yeah, sure. I mean, here, for example, I have this effect. It's not in the 95% confident, 95 credibility region here, and here it's us. Yeah, sorry.
Do the probability distributions that track each other? Or
Yeah, they are more attracting each other here in this case. But when I have here, in this case, for example, I think this is one of these signals which are very weak. One couldn't be identified. That's why I'm working in model 99, the weakest one. And the two weak ones, this is one of the very two weak ones. And this is another. This is the one that concords with this one. And another. These are, I think, the one that are closest in frequency. Less than half Nyquist step. So I ran another series of simulations. I created a sequence of data sets where two sinusoids were slowly merging together. And then instead of calculating the probability, the posterior probabilities of the parameter, I just calculated the posterior of the number of sinusoids estimated in the. And so I used different phase shifts between the signals, 0, pi half, and pi. Then I used two different. So these are 12 simulations. So three different phase shifts and two different amplitudes within the same noise level. I think it's 1 or something. Which comes. And I also used different priors because initially I used, instead of the G prior, uniform prior, and also just compared the effect of using a uniform prior. The uniform prior is actually not appropriate for this because you have this harsh cutoff. And when you use a normal distribution on the two amplitudes, this concords to have a uniform prior on the phase, which is natural, but not when you have a uniform prior on the two amplitudes. but I still ran some simulations just to show this. So again, I have data 1,000 samples, and I slowly approach the two different sinusoids by 1% of the nyquist step. So on this, I ended up with this. This is the left one is signal to noise ratio 2, the right one is 4, and so this is the distance between the two frequencies, and the green one means I have model 2, which is the correct one. So I have two sinusoids. So model 2 should be the one that identifies correctly the two sinusoids. That's the uniform prior. And as you can see, when in the phase shift of Nord, I approach like this threshold of having just 20% of the nyquist step in difference between the frequency, then model 1 is preferred, and here only one sinusoid is identified. And when I have phase shift of p half, p over 2, then this threshold is a bit lowered, and here even more. And when I have a phase shift of pi, then I can also end up with model 0, because they, when they are too close, then they just annihilate each other. And yeah, when I have stronger signal, the threshold is even further in the lower part. And this is a G prior. As you can see, sometimes it even happens that I have model 3. So there were like 3 sinusoids identified, because the G prior.
One of them is the difference? Or
No, they are just 3. This is just wrong. The problem is the G prior. When you have just 2 signals, then the G prior adapts to the just 2 signals. So the scaling is very low. So then the posterior even is more likely to have 3 signals, because the actual when the hyperparameter G is very small.
where is that third signal? What frequency?
I haven't shown any frequencies. Just this is just the.
You don't know.
Yeah. This is each a simulation. That's each. You know, I should have plotted maybe, but this was just the number of models I was interested in, rather than the actual posterior distribution of the parameters. But you can see, and then when the difference in frequencies increase, then I have more like a normal condition here, that I have model 2 preferred. So conclusions is capable of resolving sinusoids with frequency gaps smaller than a nyquist step. Confidence intervals can be given, or credibility regions can be given. And the advantages of estimating the number of the sinusoids and the noise variance. And also works with non-equidistant time intervals. So the computational time seems to increase linearly with the number of signals. But it's a bit deceiving, because this is given that. So when I have 100 signals, it takes usually twice as much time to simulate than 50. But given that I have the same data set, like 1,000 samples. So the longer the data set, the longer it takes time for the likelihood to be computed, and it basically it's worse than linear, computational-wise, but not iteration-wise. And so the model needs to be expanded to more realistic signals, and so the outlook is to make the signals more realistic, to include the Doppler shift due to orbital motion, and also laser sensitivity changes with orientation. So it's much more complicated, I know. So, but this is just like to sound out the possibilities to use reversible jump techniques on this. But I know the difficulties here.